Before this, we were talking about energy conservation, and we had this idea working through most of everything that the total energy of our system was going to be conserved. Now we're going to look at what happens when that's not true. To do that, we are going to consider non-conservative work. Non-conservative work is work done. Remember, work is a change in energy. So non-conservative work is work done by a force that is a non-conservative force, which isn't particularly helpful as far as definitions go. A conservative force is one for which you can write a potential energy function. If I have a ball and I hold it a meter off the ground, and then I drop it and I pick it back up to a meter off the ground, it's got the same potential energy as it had before. If I throw it at the wall, let it roll down the street, go pick it up and bring it back up to a height of 1 meter, it's right back to the same potential energy it had before. There's no change because of what it did. It's just at this location, that's what it's got. Same thing is true for a spring. If I take the spring and compress it and then let go and then throw the spring somewhere and bring it back and compress it to the same as where I started, I will have the same energy as I had when I started stored in that spring. Things that are not conservative, things that don't have potential energy functions, would be things like friction, air resistance, drag of any kind. So I'm going to say friction, etc. We'll also have extra forces that we apply to a system. If I push on a block, then I'm adding energy into my system. That's a non-conservative work. So an external push or pull, or whatever that happens to be, can be a source of non-conservative work. So first, work. Work gets a capital letter W, and work is going to be equal to a parallel force times a distance. Let me show you what I mean by that. If I have a block like this, and it's sitting on the ground, and I pull on that block, with a force that points upward and to the right, not all of that pull is helping me out. Some of that pull is going into forward motion, and some of that pull is vertical. I'm not moving vertically. So I have a parallel force and I have a perpendicular force, which asks the question, parallel and perpendicular to what? Parallel and perpendicular to the direction that I'm moving my object. So if I'm moving my object horizontally, the work that I'm doing is going to be equal to my horizontal force times the distance. If I had, something like this, and I were trying to lift up a box by means of a rope like this, and I'm just kind of pulling up, and maybe there's, I don't know, some kind of a track or something so that this box doesn't just come flying into me. I'm trying to pull up on the rope like this. Well, that force is not all being helpful. Some of it's pulling it into the wall, some of it's going up. In this case, I would say I can again break this into components. This is going to be my parallel force. This is going to be my perpendicular force. So a lot of times in textbooks, you will see this written as work equals force times distance times the cosine of theta. And I try and avoid this just because if I'm given the right angle, this works. If I'm given the wrong angle, then instead of cosine, I need sine. So if I'm going to write this equation in terms of an angle given, that is the angle specifically between the force and the displacement. I don't particularly like giving an equation in this form. I would much rather just say it's the parallel force times the distance, because that gets the point across pretty quickly. So then when I have non-conservative work, my problem changes a little bit. Before, I had potential energy, kinetic energy, initial, and final. Now, these aren't necessarily equal. So I can have my initial and final potential and kinetic energy, but I'm adding energy into the system or removing energy from the system. If I've got a box like this, and it's sliding along on the ground, then right now it's got some amount of kinetic energy because it's got a velocity. Maybe there's friction along the way. So right now what I have is I'm going to have a frictional force that works to slow me down. My displacement is in this direction. So when I write my work done by friction is going to be the force from friction times the displacement. These are parallel, so I'm not worried about a perpendicular component because it doesn't exist, but they're in opposite directions, so they get a minus sign. What this means is that friction is going to produce a negative work, and a negative work means that energy is coming out of my system. So in this particular case, I have no potential energy at the beginning or at the end. I have some amount of kinetic energy at the beginning and none at the end if I'm coming to a stop. I can add in the work, and the work here is going to be work from friction, or force of friction times distance. And then what I'm saying now, before I would say my total initial energy equals my total final energy. Now I'm going to add in my non-conservative work. And then it's still true. When I was doing energy conservation, this term was 0. Now that I'm not doing energy conservation, now that I'm letting other forces add and subtract energy, this term is no longer 0. And I just have to work with figuring out how to do that. So I'm going to give you a couple of example videos on what those problems might look like, but this is the basic idea that I have my initial energy, which would be equal to my final energy, but I'm adding this non-conservative work term. And if I can add these numbers, that means they all have to have the same units. So this thing has units still of joules. That's it. That's non-conservative work as a concept. Examples are coming soon.